Welcome to this chemistry lesson where we'll explore the Van't Hoff factor, a crucial concept in colligative properties of solutions. The Van't Hoff factor helps us understand how solutes behave in solution compared to their expected behavior. Let's start with a simple definition. The Van't Hoff factor, represented by the letter I, is the ratio of the observed colligative property to the calculated colligative property based on the solute's molecular formula. We can write this mathematically as I equals observed value divided by calculated value. But what are colligative properties? These are properties of solutions that depend on the number of solute particles, not their nature. They include boiling point elevation, freezing point depression, osmotic pressure, vapor pressure lowering. The value of the Van't Hoff factor depends on how the solute behaves in solution. We can have three main cases. First, when I equals 1, this means the solute neither dissociates nor associates in the solution. It behaves exactly as expected from its formula. For example, sugar, C2H220, in water behaves as a single unit and doesn't break apart. Second, when I is greater than 1, this indicates that the solute dissociates in solution, creating more particles than expected. For instance, sodium chloride, NaCl, dissociates into Na and Cl ions, doubling the number of particles compared to the formula unit. Third, when I is less than 1, this suggests that the solute associates in solution, forming larger units and reducing the total number of particles. For example, acetic acid, CH3COH, can form dimers through hydrogen bonding, reducing the effective particle count. Let's work through some detailed examples to better understand the Van't Hoff factor. First, let's consider sodium chloride, NaCl. In water, NaCl completely dissociates into Na and Cl ions. For 1 mole of NaCl, we expect 1 mole of particles based on the formula, but we actually get 2 moles of ions, 1 mole Na plus 1 mole Cl. So the Van't Hoff factor for NaCl is I equals 2 divided by 1, which equals 2. Now let's examine magnesium chloride, MgCl2. In water, MgCl2 dissociates into 1 Mg superscript 2 ion and 2 Cl ions. For 1 mole of MgCl2, we expect 1 mole of particles based on the formula, but we actually get 3 moles of ions, 1 mole Mg superscript 2 plus 2 moles Cl. Therefore, the Van't Hoff factor for MgCl2 is I equals 3 divided by 1, which equals 3. Note that these are ideal values assuming complete dissociation. In real solutions, especially at higher concentrations, the observed Van't Hoff factor may be less than these theoretical values due to ion pairing. The Van't Hoff factor is crucial for accurately calculating colligative properties. Let's see how it affects the freezing point depression. The formula for freezing point depression is delta T underscore F equals I times K underscore F times M, where delta T underscore F is the freezing point depression, K underscore F is the freezing point depression constant for the solvent, M is the molar concentration, and I is our Van't Hoff factor. Let's compare the freezing points of 3 different solutions, each containing 1 molar concentration in water, K underscore F equals 1.86 degrees Celsius per M, sugar, C2H220, where I equals 1, NaCl, where I equals 2, MgCl2, where I equals 3 for sugar. Delta T underscore F is equal to 1 times 1.86 degrees C slash M times 1M equals 1.86 degrees Celsius for NaCl. Delta T underscore F is equal to 2 times 1.86 degrees C slash M times 1M equals 3.72 degrees Celsius for MgCl2. Delta T underscore F is equal to 3 times 1.86 degrees C slash M times 1M equals 5.58 degrees Celsius. As we can see, despite all solutions having the same concentration of 1 mole, they have different freezing point depressions based on their Van't Hoff factors. In practice, the Van't Hoff factor is often determined experimentally by measuring colligative properties. For strong electrolytes like NaCl, the theoretical Van't Hoff factor is 2, but experimentally it might be around 1.8 to 1.9 due to ion-ion interactions. This happens because not all ions behave as completely free particles in solution. Some temporarily pair up, reducing the effective number of particles. Additionally, the Van't Hoff factor changes with concentration. As concentration increases, ion-ion interactions become stronger, causing the observed Van't Hoff factor to decrease from its ideal value. In summary, the Van't Hoff factor is a crucial concept that helps us understand how solutes behave in solution and affects all colligative properties. Key points to remember. 1. The Van't Hoff factor tells us the ratio of actual particles to expected particles. 2. For non-electrolytes like sugar, I equals 1. 3. For strong electrolytes, I equals the number of ions per formula unit. 4. In real solutions, experimental values are often lower than theoretical ones. 5. The Van't Hoff factor decreases with increasing concentration. Thank you for watching. Remember, understanding the Van't Hoff factor is essential for accurate calculations of colligative properties in your chemistry studies.